Hello everyone, so in this video I'll show you another example of the Bibliometrics package of R, and I will use the data which deals in the nexus of supply chain and marketing. So here is my R studio. This is how it looks. Normally I will get the outputs in here, the console, and here all the new data files that will be created will be stored here. And here you can see the file directory, plots, package. You can install package and view other things, and here you will write the codes. So this is how it looks, and we will make another video on R, how introduction to R. Then in that video you can see more detail about how R works. But okay, today's focus is on this Bibliometrics package. So I already have installed the package, but if you have not, then go here, package, click install. Then you just write Bibliometrics and then click install. So then you will have the package installed. But I have installed the package, and as you know, in R you have to run every time a package before doing the analysis. So I will run it. So to run, you command library and the package name. So I ran the package, and I have my data is stored in this path, and the name of the data is scopus.bib. I'm using bib text format data, and this is how we read data. So I will click, so you will see the data will be stored here. It's here now, and we have to convert this bib text data to a format which is given by this Bibliometrics before doing all the analysis. So to convert the data, I'll click here. So here actually you can change. Now I have here Scopus. You can also change to ISI, and this format here could be also changed, and you can actually see what formats are supported by this. And to see that, you can actually just copy this. Just wait a minute, because it's running this code. This conversion is running. Let me show. Yeah, let's wait to get it converted first. Yeah, it's as you see, it started to extract. So 100 is done. Yeah, soon. Yeah, it has like 1311, I think. So yeah, it will be done quickly, I guess. So as you see now, the conversion has been done, and we have a new data file here which is named as M. So you can actually change this name. You can give any name you want. And yeah, so we have now 1311 observations and 21 variables. You can actually have a look on this as well. So here you will see that all the variable names we have. So the articles, article titles, journals, this is source, so the journals, and type, yeah, all the information are here. Okay, so we'll work mainly with this data set. And here, as I was telling you earlier, so you can see what can you do with this convert to df command. Okay, so to do that, you can just quickly run help and then the command. Then you will see here detail about this. So as you see that we used Scopus, right? But you can also use ISI. If you extract data from ISI website, then you can use the command ISI. And the formats are bib text, plain text, so this format can be also changed. So let's go to analysis now. So to get some basic results. Okay, before actually I go to some analysis, I would like to show a few things. So this is the website of the Bibliometrics, bibliometrics.org. They have updated a few things. You can scroll and see what are the new things, but what I suggest you that you go to these documents. Okay, so here they provide you a lot of things. So I would I would suggest you to have this reference manual. This reference manual, you should save it, and this has everything. This you can, whenever you are stuck with a command, you can read through it, you can find it, and you can this will help you a lot actually. So you should have it with you. And then also they have some tutorials. So they also have some tutorials here, how to extract data, how to use it. And what I would suggest to you is that, a lot of the things they have written in detail here. So you can read from here a bit when you need, and this will help you a lot with a lot of things. The meaning of some comments, what actually it does, this kind of things you can read. And if you scroll down in the end, what I would like to suggest to you is that you should actually read these papers, all of it. So because these are the base of this package and how it works. So I'd suggest you to read all of this. So now let's get back to where we were. So we'll do some analysis now. So the command is that this one you can actually write anything you want. So we wrote results. We actually took it from the Bibliometrics package itself, and this is the main command for this analysis. So you run this command. So it will give you basic bibliometric analysis, and of course you need to run a summary command of the results. In R, it's often like this, that you first run the command and then you have to give a command to get the results, which is summary or describe, like this kind of commands. And we'll click the summary command, and now we'll have a lot of results. So we can click here to make the screen bigger. Go on the top. So here are some basic results, as you see: number of articles, sources, years covered, for your citations, then annual scientific production, most productive authors. We have total top manuscripts per citations. We have most productive countries. USA is the top. Then here you see the single country publication. So out of the 327 published by United States, 270 are actually single countries. So all the authors were from US, and then the rest is from multiple country publications. Then total citations per country, again US is the leading one. Most relevant sources, the journals, supply chain management, European Journal for Operations Research, these are the leading ones with the number of articles. And most relevant keywords, so these are the keywords and used in number of articles. So that's what we get from the basic bibliometrics analysis, and we get back to our codes again. So this information that we got from this command, we can actually plot them. So to plot it, we run this command. I have written down the commands in advance so that I don't have to write at the time. So I suggest to you that you write one by one and understand how it works. So I'm gonna run it, and I will see a lot of plots here. It's running, and it takes some time. It's a lot of data to process actually. So here I get the plots. So this is one plot. Then if I go back, I get another plot. Average article citation, I get another plot. Annual scientific production. So all the results we got here are now plotted using this command. Most productive countries, most productive authors. This is what actually you get. So if you were to make it larger, any of them, you just click zoom, and if you want to export them, just go here and export as image or PDF. Okay, so now we get back to some analysis of cited references. Which articles were most cited by these 1311 articles? So to do that, we'll run this code, because M is our data set. So from M, if you remember, we have a variable CR. So I can just quickly show you. We have a variable here which is called CR. Here, CR. So all the citations of this article is here, CR, cited references. So the citation of this article are stored in the variable CR. So it's for all the articles. So now we can we will go to CR and we will run this command CR. Then we want to see the field articles, and we want to see the top 10 because there are many, they rank all of them. So we don't want to see all of them, we want to see only the top 10. So this is how it works. Yeah, it's processing the previous command. Yeah, so we get 10 articles here. Yeah, here you see. So 10 articles. These are the most cited articles in this among these 1311 articles. Yeah. So the most highest one is this one. Morgan and Commitment Trust Theory, Journal of Marketing. Anyway, so you can do the same for authors, most cited authors. We can again get the top 10, the most cited top 10 authors. Then we could also do this for local citations, but it works only with it works only with the Web of Science data, but we're using Scopus, so this command will not work here. But we can do this dominance ranking here. So here we get the dominance ranking of the authors. Here I have mentioned 10. You can do 5. You can do 20. Yeah, it's up to you. We can make it 15 if we want. So here we have 15. And how it is calculated, to see this, please read the manual. You will see. Read the Bibliometrics manual. You will find it there. And then you can calculate author's H indexes. So you can take any author's name and calculate their H index. For instance, Kurata, he is here, Kurata H. So we can check his H index, calculated here, G index, M index. Yeah, so you can get his total citation index, where he published and how many citations he got. So you can just change the name of the authors, and then you can create their H index. Then to calculate the H index of the top 10 most productive authors, you can just do it as once. We can just run this code and we'll get it here. Here is it. So we have to run these 3 code at the same time actually. So you run these 3 and you get this top 10 authors. Then we can also calculate Lotka's law coefficient. So to do that, we just run this command Lotka and results, and you can get productivity information. You can get the beta. You can get a constant. So you get all the information. You can get the R square for Lotka's coefficient, and then you can also get the p-value. So now we can also compare the distribution of the publication. So we can calculate the observed distribution, and there will be a theoretical distribution. Normally there is a theoretical distribution of publications by authors, and how many publications should the author be published, the top ones, and this is the equation. I don't really know at the moment detail about it. Please go read about it in the published articles, in the most recommended articles. But we can plot it and we can see. So here we first have the theoretical one, and then we will also add the observed one, and we can add a legend here, theoretical and observed. So we see actually the data we have here, it actually follows very well this 1100 and this 1311 articles. Here the observed and theoretical distribution of authors' publication follows, observed and theoretical follows a similar pattern. So it's good, I think. So here we can also do some bibliometric coupling. The command is Biblionetwork. So we can do coupling, we can do co-citation, we can do collaboration, co-work, a lot of things. So let's first go with coupling. Here it is. So now we are actually done. This code ran. It took some time. So now we can actually see what more we can do with this command of Biblionetwork. So we wrote help and then bracket Biblionetwork, and we got this window here. So here we can see actually what are the arguments that are possible. So for network, you see we can use here authors, sources, countries, author keywords, titles. So we can use actually, yeah, all of it. And then for analysis, for this place here, coupling, as we are using now, we can actually use collaboration, cohort, co-citations. I'm showing examples of all of them. The first one is the coupling one, and we run this code with network plot. We'll get a plot out of this. It should be, yeah, the plot is here, so you can zoom in to see in detail. So we see the authors coupling here. We see different colors, and based on different colors we can see the grouping here. And we can also use co-citation. I'm running, yeah. You can actually run both of them together. You can even run all of them together, but I prefer to go one by one, because then I can, yeah. So co-citation here, and it doesn't really look good, but you can actually play with the type here, and with the size and number of articles here, and then you can get a better one. I'll just proceed with the country. Yeah, it's yeah, authors collaboration network again. But yeah, it's based on collaboration, authors collaboration network. So I will run it, and so we see the collaboration network of authors, how, with whom, who's collaborating with whom. I think this is very interesting. And then we can also make a country collaboration network. For that we have to create another data set. I will name it M2. Here I will use M2 again. So because we are already having one data set as M, so I will just make another one. So we are using data from M, making a new data set here. So it will appear here, you will see. Yeah, 2 is here, but we'll use this to make this country plot. That's done, and this code is a bit long, as you see. Level size is 0. So I could play with this a little bit, but I don't want to play at the moment. I will just run as it is, and we get another, yeah, the country collaboration. So here you see US is the biggest one in publishing, and we see the, yeah, linkage between the country collaboration. Maybe we should use less number of countries here, to then we'll see the linkage is better. Okay, so now we move to keyword occurrences, and we again run the command. Here we change it to keyword occurrences, and then when, yeah, it is running, done, and we will run the plot. So we'll get another plot here. It's taking some time. Yeah, keyword occurrences. So here we see marketing is the largest one, supply chain management, as we are trying to see the nexus, the interaction between supply chain and marketing. So yeah, this two should be the dominant one, but then we see others like game theories, optimization, profitability. Yeah, some are more leaned towards supply chain, some are more leaned towards marketing. Then we can actually run this command, conceptual structure, to rebuild the conceptual structure of the field. It took some time to run this code, but in the end it ran. But the image is supposed to appear here soon, but we cannot see it yet. So I was waiting a little bit, and now the image appeared. It already looks very messy. If we zoom, then yeah, it's again taking some time. So we see that it's really a messy one. It's yeah, we can't. It says there are 4 clusters, but I can't really see anything. It's too messy. So what I can do is I can again go to this help, and then this command to see what are the other options I can have here. Here the field was DETM. What does that mean? DETM means author's keyword stems through Potter's stemming algorithm. Maybe I can use another algorithm. Maybe I can use only DE and see what I get. So we got something here. It still looks very messy. Let's have a look. Here at least we see something. This one is one field. This one is one, and then here we have another one. But it is still very messy, and I don't really like it too much. Maybe I'll try one more here. Let's say AB, terms extracted from abstracts. AB. So when trying with AB, actually it takes forever, so I'm gonna stop it. Yeah, and maybe I will use simply ID. But it's not even stopping. Okay, so when I actually change the structure here, the field to AB for conceptual structure, my R crashed, but now I'm changing to ID, which will work based on the keywords. So let's see what we get now. So yeah, actually after changing the field to ID, I expected to get something more meaningful, but from here I can see I got something even less meaningful. It's even worse, you know, than before. So it's too messy. So maybe using DM was the best. Or let's see. Now here I cannot really read anything. Maybe using maybe using the DM was the best, or you have to try more combinations here to see if you get something more meaningful. And when you get a figure, nice figure here, then it's not only that the figure is useful, you have to read the papers and you have to explain why they're grouped together and all these things. You know, that's when you make some scientific contribution. And here there are two more comments, historical and these plots, but unfortunately this works with only Web of Science data. So that's all for today. Thank you for watching this video. So if you find it useful, like, comment or share, and subscribe to our YouTube channel.